Okay, well, let's go ahead and open up in prayer. It's nice to see everybody's enjoying Halloween and in a good mood. So let's go ahead and invite the Lord here. Dear Heavenly Father, Lord, pray that you would be with us today. Pray that you would be with each of the students. Help them as they're learning a lot of really interesting things here at APU. Pray that you would help them to prepare for their future profession. Also, Lord, I pray that you would help them in their spiritual formation, Lord, just the amazing truth and wealth of information we can gather from Scripture. Pray that you would help them to really drink deeply from that and become more and more aware of the theological concepts we want to be guiding our lives by, and some interesting and creative ways for faith integration as they move forward. In Jesus' name we pray. Amen. So apologize for having some technical difficulties here. But the normal way I project things in the class didn't seem to be working, so kind of had to go grab a old school VGA cable. I remember when that used to be the big thing that was used all the time. So what I wanted to cover today was we've covered a lot of ground in our lectures. And so now we're moving into this next major section where we're going to be talking about looking at stuff that's closely centered on the CPU. In a way to begin that discussion is to be thinking about the instruction sets. And we actually get exposed. Stalin is going to start talking about assembly language. And so this first lecture will help to give a perspective on that. I wanted to say thanks to Avery on another thing. I'll show that after I go through some lecture material, and also on Thursday where I'll actually demo it. But for those of you that like using VS Code, I found an alternative to the Mars MIP emulator. You can actually do your programming in there, so that might give you an IDE that you guys are familiar with. And by adding a extension, Avery was to find the right extension. And so that's a little bit of a nice heads up on that. I did post that in Canvas, so if anybody hasn't found that, I'll show that in a little bit. So first of all, let's quickly just remind ourselves where we're at. And so we see this basic structure of the computer architecture, the von Neumann architecture, and you could argue it goes down several layers. We've had a couple digressions talking about hardware, how things have changed over time in terms of computers. Some things still scale linearly, some things have flattened out. We talked about the main elements, getting in a little bit more detail, that you have registers and stuff like that in the CPU. A thing that will be more important for us to be considering is something called the arithmetic logic unit within the CPU, various ways of how the memory can be viewed. And so basically from an other element in the architecture, you can translate it. And so it doesn't need to be exactly the way a CPU sees it, but and so we've got a chance to be exploring input and outputs, memory, and now we'll get even more into the CPU. So the basic execution is the fetch execute, and what we're going to be seeing in the material that we're covering today, we're going to get a lot more detail about that. And so hopefully that will help to fill in some gaps if you're still trying to figure that out. We spent a lot of time talking about how you can improve performance. Caching and buffers are some of the places where things like that can actually benefit us. We talked about different types of things like a hard drive. Maybe some of you might still have a hard drive that actually has these platters on it. Otherwise, you probably have a solid state hard drive. We talked about RAID levels and how things are done to try and have higher levels of data integrity. The most robust way is that literally a mirroring. So two disks have exactly the same information, but there's also some things in between where you actually have various forms of error correcting, ways of checking the integrity. And you can actually, if you do have some errors, you can actually figure that out if you have enough error correcting. And so those are strategies that show up in multiple levels. So just kind of moving forward, we talked about IO modules in a lot of depth. We then started to get into number conventions. And so it's real easy for us to think in a binary 10 way of how we do numbers, but that similar strategy can actually work in binary. And so anybody want to take a guess if I was to convert this to binary, what value that would be?
4, 2, 1.
Yep. So a plus floor plus 2 plus 1. If you see that, so 2 to the 0 is 1, and there's 1 there. So there's 1. 2 to the 1 is 2, so there's 2. So 8, 4, 2, 1. Add that up and you get 15. So that's where something like this can be helpful for us to remind ourselves what the conversion from one system is to another. And I already mentioned the ALU, really the Swiss Army knife of the CPU, the thing that makes it programmable in some pretty interesting ways. We talked about floating point formats, and so there's actually a standard IEEE 754. And so you can either have a 32, 64, or 128-bit format. And we mentioned how you have two possibilities. With a significand, this tells you what resolution you have. And with the exponent, that gives you the dynamic range. And so if you start to add more bits to the exponent, it means you're going to have less fidelity in that number, but you're going to have a larger range. So if we're limited by a certain number of bits, that's what we have there. So a couple other ways of thinking about that. We then started to talk about Boolean algebra to give things a pictorial way of considering what we've already talked about. We've had a chance to work with logic gates, and so that's something now that you have some familiarity with. And there's some interesting things of how you can put these together. And when we were going over chapter 12, we saw a couple different ways that you can get to this output. Say this is what you would like. You could simplify this, and thus we have Boolean algebra. Or maybe these interim products are useful, and so maybe this is more elaborate. That still might be something you want to be doing. We introduced the concept of an FPGA, a field programmable gate array. This is what it is like here. This is an example. You've specifically programmed it so that these interim outputs and the final output is going to produce what we have here in this table. And so this is when we get to the material we're going to cover today is now we're thinking about things in an instruction set. And so I'll just go over to the regular lecture notes for today to catch up those details. So thus we have the first of 3 chapters that talk about instruction sets and thinking about things from an assembly language point of view. So there's different things that need to be considered in machine instruction characteristics. We want to be thinking of the elements of a machine instruction. And since we've started to do our assembly language, you're getting a chance to see that real time. And most of you have already finished that, but we'll do a little bit of review on that. We want to be thinking about the various ways of how we represent the instructions. What are the instruction types? What about the number of things that are associated with that instruction? And what about instruction set design? We'll be thinking about the x86 architecture as well as the ARM. We're actually doing some programming in the ARM architecture, but both of those are theirs. And so once again, we have to be thinking about numbers, how we're going to be handling characters. ASCII is maybe a standard that you're familiar with. I'll introduce the international name, which is one that I'm not as familiar with, but that's useful for us to know. And so that's just a quick overview of the things that we'll be getting a chance to get some insight for here. So for machine instruction characteristics, the operation of the processor is determined by the instructions it executes, referred to as machine instructions or computer instructions. So this is where we're having to think how a CPU does things and rather than having things how we would view. And so we're getting a lot closer to that perspective. The collection of different instructions that the processor can execute is referred to as a processor instruction set. And so do we want to have a lot of instructions? So make it real flexible? That tends to be more of the approach that the Intel x86 architecture has, or something that's more constrained. It's more what the ARM architecture has, and everything has the same number of bits rather than various lengths of instructions, which is what the x86 architecture has. So each instruction must contain the information required for the processor for execution. And so it looks for specific formats. If it's not going to be in that format, it's going to give an error, and you don't want to have that happen. So these, as I just mentioned with our introduction, these are the kind of things that we have. You need to be doing instruction fetch. And so we have to calculate what the instruction is. We have to figure out if there's any addressing schemes that have to be added to it. So, and then you get all of the things set up. So it's in the exact format, just ones and zeros ultimately is what it has to be converted to for it to work in the CPU. So for the operand, and so this is the thing. So you're doing an add, you're doing a move, you're doing a store, something like that. And then you have the operands. And so these are the things. Now you know that if you're doing an add, well, what are the things that you're going to add together? And so you need to be figuring this out. And so, and then after you've done that, you needed to know where you're supposed to put that information. Are you going to put it in a register? Is it going to go directly to memory? Is it going to be shipped out in I/O? Those are possible things that can actually take place. So here is just a summary of the source and result operands that can be in one of four areas. So it can be, you're connecting either to main memory, or a way of thinking about that in terms of a virtual memory, where the CPU doesn't need to know exactly what's you have one or two sticks of memory, but it just needs to have a pointer that it can consistently go to. It can go to an I/O device. So maybe you're connecting with here, like I'm connecting with my mouse pad or a keyboard, your whatever. You could be communicating with a register. And so those are the closest and fastest things that you could be communicating with. And then we had this other thing that may be new for you, this idea of having immediate. And so you'll see examples of instructions that have like a number specifically. So you're not specifying a register, you're not specifying a memory location. They'll say like a number 10. And so that's what this is referring to, this thing that's called immediate. So we're going to get more and more specific, but here's just a general way of thinking of a instruction format. And so you have the opcode. So add, say it's 1000 would be it for add. For subtract, it'd be 1001. And so there's a unique bit sequence that has whatever that is. And so for this sample instruction, we're saying that there's 4 bits that are used for the opcode. And then we have operands. And so we can have a way of pointing to that information, or of 6 bits. And so 6 bits for 2 operands. And so we have a total of 16 bits is what's laid out. So here are some examples of the kind of things. So we went through the digital logic of how you could do an add, a subtract, a multiply, and a divide. We also looked at that from how we would create an algorithm to actually perform those things. You need to have carryover. We talked about doing two's complement, and so subtraction is actually doing an addition with a two's complement. With multiply and divide, it gets a little bit complicated. They either do a shift in adds, or shift in two's complement and add. And we have those things, even though they're complicated, they're well defined. And so we know what those are. Plus, we need to do loading. We have to put things where they're supposed to be and where they're supposed to go at the end. So those are the kind of things that we're trying to specify with the instructions. And so we can have the data processing. So this could be arithmetic operations, doing Boolean operations. Some of you did that in your digital logic, and then we're trying to reflect that in what you did with your MIPS processing, assembly language processing, data storage. You're moving things to and from data. You can be moving things, data movement. So this can be dealing with I/O in one form or another, or control. So you're trying to do test to the instructions, so branching or stuff like that. So is it less than or greater than? And you have different things that you would do depending on what those results are. So here you have a couple possibilities. And so how many instructions do you have? And so what I showed you for a basic generic one, this had 2 operands. Well, what if I had 3? And guess what? If you have 3, it's only 4 lines of code. If you had 2, it's going to be 2, 4, 6 lines of code. If you only have 1, it's 1, 2, 3, 4, 5, 6, 7, 8 lines of code. So you can see this is a trade-off. Do I want to have 2, like I showed in that example before, that maybe that's the middle of the road? Or maybe I want to have the minimal amount of complexity, and so I only have 1. And so if I only have 1, then I can have 12 bits rather than 6 bits. And so that might be useful. So what is the right answer? The answer is it depends. It depends on what you're trying to do with your architecture. And so now as we get towards the latter part of the course, we'll be thinking about that. We'll have some of these lower level tools. We can then start adding it together and see what that might be in terms of the best scenario. So so this is just trying to now thinking about what we might do, say in branching instructions or stuff like that. And so this is just giving us a little bit more information about how that might work. We have like a sample here. Let me see where it is. Yeah. So I just went over this. You can see how with 3, we can easily just handle a fairly complicated argument rather than having to break it down into more and more pieces. And so that is the kind of things that can help out when we have multiple elements that we're adding. So say 3 address instructions. So that probably would be worth it. It might make it a lot closer. My experience with doing assembly language programming, I could use a lot of the techniques I could do at a higher level. And you can't do object-oriented type of programming, but for things other than that, for some of your basic type of programming, I think you'll see some analogies that you could use across the board. So what do you want to put into your instruction set? And so this can be complex because it affects many aspects of the computer system. So a cause and effect, you tweak something, you find out, well, that did help here, but it had some unfortunate side effects. You can see that every time that there's a new processor that Intel, AMD, Apple, or whatever, they take these into account, and we'll have 1 or 2 examples in the stuff that we talk about here. So you want to define many of the functions performed by the processor. The programmers means of controlling that processor. And so this is what it starts to boil down to the operation repertoire. So cat it into some major categories and then have more specifics. What type of data types? And we'll get into that a little bit. What about the format? So some of this may be a little bit strange, like you can see this. You have things going, rather than A plus B is put into C, you have the output being the first parameter and the inputs being coming after that. So that can seem a little bit complicated. Registers, how many registers are enough? For what we did with the MIPS emulator, we always had 32. And so that seems like maybe an adequate number, but the answer is, once again, it depends. And what about addressing? How much memory do you need to access? And so these are just all of the kind of things that need to be considered. Addressing, characters, numbers, logical data, all of those are stuff that are within the mix for us to be thinking about. So then just one at a time, we can be unpacking that a little bit further. For numbers, one way that you can be storing numbers is something called binary coded decimal. We'll be coming back to that and seeing that in a couple of charts here. We talked about floating point characterization. That was something that you could do. You could do integers. And so you don't always need to have floating point. And so those are just some examples of the types of formats. And so this is what I mentioned before, ASCII. And we got a chance to see that a little bit with the Mars emulator, when you can go either from digital to hexadecimal or showing things in ASCII. And so the international term for this is the International Reference Alphabet, but I'm always used to thinking in terms of ASCII, but I guess you could say this is definitely a US centric way of thinking about it. But now we're in a lot more of an integrated international community, so maybe using IRA might be better. IBM also has another one, so EBCDIC is another example of a code. But anyway, ultimately, you do need to have a translation going from ones and zeros to something that we're familiar with, because we don't think in ones and zeros. So logical data, true or false, and you can have that same type of thing for every bit. And so thus we've seen a couple examples here, numbers, we've talked about characters, logical data. And so then when you start to get a table like this, about, well, what are the different data types that you want to be thinking about? This is based on experience. So I mentioned this binary coded decimal. That's one of the things that are here. Integers and strings, all kinds of things. And I'm going to get back to SIMD. I think I mentioned this once already, but this lecture will get into that a little bit more detail. And so you have these different classes of things that you're trying to encode. And here you can see, well, how many bits does it take to do it? And so you can see that some of these are going to take a lot of memory and others not so many. And so if it doesn't take so much, you could be actually having a whole bunch. So say with a MIPS architecture where you have like 32 bits or 64 bits, you could start to put more in one byte. And so that can be an advantage. So this is the one thing that the sample assembly language textbook that I shared. It talked about a 32-bit mode, a 64-bit mode, and also something called the single instruction multiple data, SIMD, data types. And so this is something that becomes useful for multimedia. And so this is something that Intel decided this would be a great way to do that. Direct memory access, DMA, is something I had mentioned before. And so this is an example where that starts to boil out. And so you have single instruction. It can have these ways of just being broadcast into a lot of different ways that could be useful for media. And so this is now not only thinking about the Intel approach, this is the ARM approach. And so they support, it can either have an 8, 16, or 32-bit lengths. We saw with the Intel based that they had something similar. So you'll see some overlap in terms of the data types. It's going to be doing alignment check. You need to make sure that you get the bits for what you're looking for, and not one bit over. And so that's something that's going to be important. For all three data types, an unsigned interpretation is supported in which the value represented an unsigned non-negative integer. So I'll just go back to this chart since it's easy to see. So I could have 32 bits and I could potentially be interpreting it more than one way. And so maybe as a really smart programmer, maybe I can be taking advantage of this to either have a regular interpretation or an unsigned interpretation that I'm actually taking the lead, if you will. Some scientific computing, they'll have their own kind of format bit by bit. And so if you're trying to read that into a word processor, it's not going to understand how to interpret that. So anyway, so those are just a few thoughts just to give some perspective of the various types of formats, thinking both about the Intel approach and the ARM approach. I'm going to skip this, but there are more details in the textbook. So let me just kind of keep it at a higher level to start out with. And so what are the general classes of instructions? So data transfer, that would be something. Arithmetic, and so addition, subtraction, multiplication, division, all of those things are the basic things that we want to make sure that we cover. Shifting and rotating, I'll have a chart in a few slides that will give you some perspectives that you can have multiple ways in which you're going to be shifting. And if you are shifting things in a register, what do you feel if you start to have things moved over? Then we have these logical operations. Now you're more familiar with these, an or, a not, or a nor, an XOR. All of these type of things are available to you in terms of an instruction. Transfer of control, and so this is where we get into some branching. And so you need to have a some type of way of having you subtract things, you compare things, and you either jump to another location or you continue processing. And finally, you have input and outputs. You can move things to memory. You can take things from memory. All of those are the type of things that are available. So there are various processor actions for various types of operations. And so this is just a table that's trying to show you some of that, just to give a more complete way of being sure that we are aware of that. So data transfer is one of the things that we need to make sure that we're able to do. It's a most fundamental type of machine instruction. Move or would be an example, load or store, stuff like that. So here are some examples from an IBM, some of their instructions. And so we can see load, load, load. And you can see that it's not just one type of load. And so am I loading a half word, a short, a long? So these would be integers, characters. And so all of this gets into some of the specifics. And so even when we were looking in the help field for the Mars application, you can see that there were, say for add, they had like maybe 10 different versions of that add. And so that's what it is like, what are you adding? And so you have a little bit more fidelity. So most machines provide the basic arithmetic operations. And so we can be doing all that. Other possible things are taking the absolute value. And so if you have the 2's complement, you would have to undo that. Or you want to take the number you take, convert it into a 2's complement. You can invert it. So, or you can increment, decrement. Those are all things that are available. This is just a logic table, stuff that you guys are familiar with now, but this is just thinking about how you're going to be comparing two inputs. And so if I wanted to do a logical operation, this would be the kind of results that you can get. So a not command, an and command, an or command, an XOR command. Those are the types of things that we can be doing. And another comparison, if they both are 0, it gives a 1. If both are 1, it gives a 1. Otherwise, it gives a 0. So I made this a little bit easier to read. And so this is like a shift. And so if I do a logical shift right, well, I need to put something in that digit. There's nothing there. So you start padding it with zeros. Or if you want to be doing a shift left, we do the same thing. We pad it with zeros. Or an arithmetic right shift. And so there's something different that we need to be doing. And so say we just replicate that bit, that would be one possibility. And here we just have an arithmetic shift left where we decide to be packing it with zeros. And here we see an example of maybe a way of thinking about it. It's like a circular array. So we shift things over and it just doesn't get lost. It drops out of the bit bucket, but it circles back and does this. And so instead of padding it with 1s or 0s, we have another way. So these would be an example of 6 different type of shift operations that we could be doing. And this gives you an idea of what that would look like. So if we're going to do a logical right shift 3 bits, we can see that now we padded 3 zeros here. We've lost the 3 most least significant digits in that number. And so once again, maybe for some of the basic things that we could conceive, we couldn't imagine doing this. But what if you're trying to do image processing, pixel by pixel, or any number of other things? These could be examples of things that would be useful. You're trying to interpolate, so maybe you're going from regular definition to high definition or to 4K. You might have something like this where things you're trying to do at a assembly language level could make it an efficient way to have things do it seamlessly and look good on a monitor. So doing conversions is something that's going to be something that will have to be done. And so that's just something I just want to be pointed out in that context here. What about input and output? I mentioned this term, direct memory access. You may want to be working directly with other types of things. And so manipulating or streamlining what's going on. So say with my cursor right now, I could go into the settings and make it go faster or slower. So the sampling that it has is going to be less or more. That could be an example. Direct memory access, say you have an older computer and you still want to watch a movie on your computer. If it has direct memory access, this is one of the ways that it can start to offload some of the burden that CPU is having to manage. System control. And so there are a handful of ways of doing branching. So this is what we're dealing with for system control. Based on certain criteria, you're able to program what you're going to do. And so it can actually make those decisions based on what you programmed it, and having the branching is going to be the key element for that to be possible. So wire transfer control operations required is essential to be able to execute each instruction more than once, if that's what's needed. And so you can do branching, you can do skips, you can do procedure calls. Those are all things that are possible. And this just gives you an example of the types of branching. So an unconditional branch, so basically a jump, go to another line. You can have a conditional branch of one type or another. So say if the result is 0, so it branches, otherwise it doesn't, or branch if equal. These are the types of things that you can be laying out for possible ways of going from one location to another. You could skip instructions based on a criteria that you set up. That's all things that are possible. For procedure call instructions, this is just some more details. It can be a self-contained computer program that is incorporated into a larger program. So you can have a subroutine or something like that. That's possible. And maybe you've never thought about having a view of what your program would look like in a scenario, but you can be going from branching from one routine to another. And you can see it could be fairly complicated. And this is just giving you some insight into the execution sequence. And here we see the calls and the returns that could be taking place. You can also be using the stack. That's yet another variant. So maybe you don't need to put things into a register. You just keep things using the computer stack. And so I think most everybody's had CS260. And so one of the data structure types is a stack. And so here we're just seeing we're sticking things on the stack one at a time. And so you pop things off the stack. And so that could be another way to streamline some of your programming. This is just another view of the stack how it can start to be something that's useful. So x86 provides a complex array of operation types, including a number of specialized instructions. So their instruction set is huge, maybe like 4 times what you would find in an ARM. And so that's one of the distinctions that maybe you would like to consider for a specific architecture for your application. Do I need an ARM processor or an x86 architecture type of processor? Like I mentioned, that my Surface that I have, I decided to get an ARM-based processor just to begin to see what that might look like, to make a comparison. There's the status bits, and so we've got a chance to be thinking about the sum. If you add 2 things together, what do you do if it goes out of range? And you can have a carryover bit. If I want to be checking errors, I can have a parity is one of the ways that we can be using for that. What about sign? What about overflow? All these are things that are possible that we can be looking at. So this is now just getting a little bit more into what things would look like for specific instructions and what you would call them. And so this is just, I won't read this table, but you can look this over and get a better sense of what all that is about. And here's once again coming back to the SIMD. And so here's a little history there. In 1996, Intel introduced MMX technology into its Pentium product line. And so MMX is a set of highly optimized instructions for multimedia tasks. And so there was enough interest, and people were not just using a computer to calculate numbers or to solve an equation, but actually using it for media. So this was a huge jump, and all of the computer graphics, gaming, Some of you guys are really interested in gaming, and so that's the kind of thing that started to open up a whole another branch of computing. So they had to define some more data types to handle this. So it conveyed these things in packets in various lengths. And so a byte, a word, or a double word, all of those are things that you could be doing as you're just trying to get those from memory to I/O devices. So here's an example of some of the instructions that were introduced for MMX operations. You can see that there's not just one or two. Once again, they're being more precise in terms of what they're trying to convey with those instructions. What about image processing? And I mentioned this a little bit. And so you could be doing a bit by bit comparison, a coherent detection and between images. And so change detection, that's an example of one of the things that this type of capability could actually be useful for. So with the ARM processor, you're going to see a lot of the same things, but it's going to have a smaller set of instructions. All of the instructions are going to be the same number of bits. And so it's going to be more optimized, say, for media, for lower and not as intense type of operation. Although there are some things that are moving into that middle ground where, say, maybe we need to have some of that capability, and that's possible. So load and store, branching, data processing, multiply instructions, parallel additions, status register access instructions, and also having some extended instructions. Those are all within the realm of what's in an ARM processor. So similar to what we were showing for the x86 architecture, here we have the conditional type of instructions to branch, to do a logical check, and based on that, you either go to another memory location or you continue. And so these are just some of the things that we have here. And so this is one of the things where sometimes you have to stare at the instruction set for a while and say, what is your pseudocode? What is your algorithm that you're trying to do? And then you're going to be determining what instruction might be the best approach for doing that. So that's kind of a whirlwind introduction for the first of 3 chapters that we're going to be talking about for instruction sets. We talked about the characteristics of instruction sets, the type of operands, how are we going to put in characters, numbers, logical data. We did a comparison between the x86 and the ARM data types and the types of things that they do. And so now you have a better sense of what's going on between those. So let me just do the other thing that I mentioned I wanted to do was I wanted to say thank you to Avery for what he shared. And so I'll just show this. And then on Thursday, if Avery's up for it, I would really love to have you share what you are doing with you were able to accomplish with what you shared with me. So I think everybody, includes those online, are seeing it. And so this is how you would do it with a VS Code. There is an add-on that you need. And so I know this is true for Eclipse and probably a lot of other IDEs. There's community add-ons. And so this is an example of a community add-on. The thing that I was struggling with was getting this naming convention. I was trying to look for things in ARM within the available extensions. And so Avery, you found it. And so maybe I should have just been looking for Mars rather than ARM. And so this is now something that I put in Canvas. So let me go over to Canvas and I'll show you. So if you go under the project resources information, I updated this. And so now there's more things here. So what I mentioned that there are two possible ways that you can be doing assembly coding, either with the Mars emulator, or you can use the VS Code with the Mars code extension. So this would be good for writing your code. If you want to get some insights into how it actually works, that's where the Mars emulator, we can actually be looking at the contents of those registers. But after this course, probably a lot of times, maybe that's not something you're going to really be focusing on. You're going to be focused on getting that subroutine to do that that capability fairly quickly. And so that could be something that would not be necessary except on an occasional basis. Or maybe you actually will have access to the hardware. I started to introduce the idea of using a Raspberry Pi. So last Thursday is the first time I brought that up. And so that could be where you actually have the physical hardware, maybe not you, but you working with a team of both computer scientists and engineers are going to be fleshing that out. Okay, with that, I think I'll stop and see if there's any comments or questions.
What's the purpose of when it said load half word and store load half word? What's the purpose of that? Is that just to find like key phrases that you want to try to store and load?
Well, it's if we go back to my cursor. So it's like, well, what is that information? And so say if you have like IO, and so say you have a word that is 16 or 32 bits, but you're only using 8 of those. So maybe for that application, that's all you need. And so you're loading that. So you're going to be sending a control word to that IO device, or maybe you're going to be receiving that from that IO device, or maybe it's going to change depending on what type of mode that it's set up to do. Maybe these are packets of one sort or another. And so depending if you're, say, like standard fidelity, HD or 4K, maybe those would be examples of when you would be using one or the other. So it's once again, when you're looking at an instruction without an application, it can seem like, well, I don't see how I would ever use it. But guess what? These guys don't add instructions just for fun. It's because their customers needed a capability, and so they had to figure out how they're going to program that. And so that's what's led to having more and more instructions that are made available. So does that help?
Yes.
David? Okay, so maybe I'll just ask Avery once again, would you mind showcasing your what you developed and what you shared with me and how you got it to work? And you were sharing with me, but I'd like to let everybody else have the advantages of what you're doing. And maybe you can give your thoughts on, I know Enzo was stating that trying to do coding with the IDE and the Mars MIPS emulator was difficult. And I would imagine that VS Code would be easier for you guys to actually do your editing and compiling and troubleshooting. Does that sound good?
Yeah.
Avery? Okay. Any other comments or questions that people have? Maybe I'll just check online. Thumbs up if everything's looks okay. Oates? Okay, he may be having some comm issues. So if anybody is getting a little bit behind on some of the assignments, please reach out to me. I definitely don't want that to take place. I do have office hours on Wednesday. If that doesn't work for some of you, I'm happy to try and work out some other time. But I've also seen a lot of really neat things that you guys are developing, and so that's really cool. So I think that's a good breaking point. I'll look forward to seeing you all on Thursday. Okay? God bless.
Thank you.